Hello, everybody, and welcome to week 13, the final lecture in environmental concerns. I'm Michael Leclerc, and today we're going to be talking about aquatic environments and how they relate to climate change. We have the following topics we'll be discussing. Freshwater salination, coral reefs, algal bloom, rising sea levels, invasive species, lake turnover, and extreme weather events. Some of these are probably familiar based off of the terrestrial environment we talked about last week, such as invasive species and extreme weather events. We're going to just fine tune them just a little bit so that we're dealing with stuff from the aquatic environment instead this time. So first off, we got freshwater salination. So basically, in a nutshell, basically what this is saying is that salty runoff will contaminate our freshwater sources. And so the biggest source of this is from winter road salts that we use to get rid of snow off of our roads. Sea level rise and saltwater intrusion is another source. However, the major one we're going to be discussing is obviously the winter road salts that you're probably pretty familiar with, especially as we come out of the winter just pretty currently. Cities themselves and towns and municipalities, they all attempt different methods to try and reduce how much salt that they put down on the roads as a result of how much road salt actually can impact and change the chemistry of our freshwater sources. They can do different things such as more effective salt combinations. You have things such as magnesium chloride. You have your typical sodium chloride. There's even potassium chloride. There's a whole bunch of different chlorides. They all have kind of their own benefits and strengths and weaknesses, such as just cost is a big one that the cities are concerned with. But some of them are actually more effective at lower temperatures than other salts are. So there is a bit of a reason for that cost increase, essentially, is in a colder environment, some of these salts, such as magnesium chloride, are actually just better than sodium chloride even would be. Other things that they try and do is they'll only use salt on major roads as opposed to the residential or smaller roads. The smaller roads, they'll either just use sand or in some cases they'll just plow it straight. They won't even use salt or sand at all. They'll just plow it and clear the snow that way. Sand has its own disadvantages that we'll discuss a little bit. And then, of course, there's other things like just making their stormwater management a little more effective by increasing pipe capacities, increasing the infrastructure, adding catch basins, stuff like that. So, am I in the way of this a little bit? Just a touch. I'll get rid of myself just to get through here. So, this is essentially, in a nutshell, how stormwater management works. So, number one, we got our rain and melted snowfall. It ends up on our surfaces like roads, driveways, and sidewalks, and it flows into a catch basin. That's those guys right along the side. You're probably pretty familiar with them. They're all over the city or over the town or wherever you live, basically. And after that, they flow through storm pipes into these inflows, which end up in what are called storm ponds. The mixture of rainwater and pollutants flows from catch basins to storm sewers that lead to stormwater management ponds, which is basically what I just said there. Storm ponds work in a couple of different ways, but the main one that you're going to see is that they basically allow oil, dirt, and pollutants, and in this case salt, to filter out, similarly to how wastewater and freshwater sources work, where by slowing down the speed of the water, everything has a chance to kind of drop out, and so all of the pollutants that's in the water from stormwater will end up flowing down to the bottom. And not flowing is probably the wrong word. Falling down to the bottom of the pond, and it says there they settle down to the bottom. The treated stormwater from the pond is then slowly released into local waterways, which are your rivers, your streams, and then eventually your lakes. The way that this kind of generally works sometimes too is you'll have almost like a wall, is I guess the best way of putting it, with only the top layer of water that is allowed to get over top of this wall. And that top water or top layer is generally the cleanest because everything would have filtered out or settled out by that point. Every 15 to 20 years, it also mentions here, what ends up happening is all of the stuff has been building up in this stormwater pond, right? And as you can imagine, eventually it will run out of space, right? If it keeps building up, eventually that pond will just be full of sediment. So they come in and they actually empty out all the sediment from the pond to kind of, use some excavators and stuff to take everything out. And that gets, disposed of. And as a result, the pond can start functioning again as it did from day one, all over again. This has kind of been an advancement from back in the old days, I guess we'll say. Back in the old days, the way that stormwater management worked was they simply wanted to just get water off the streets as fast as humanly possible. So you didn't really have these stormwater ponds. You didn't really have you didn't have huge networks of storm pipes. Basically what you had was you'd have the catch basin, it'd flow directly into a storm pond, and the storm pond wasn't really a big extravagant thing that dealt with settling out pollutants and stuff. In some cases your stormwater pond was basically a stopover for like a brief moment. Sometimes you didn't even have a stormwater pond. Sometimes what would happen is the water would flow in the catch basin, and this water would have all the sand, all of the silt, all of the salts that we're talking about, and it would flow basically directly into the rivers. And that was obviously, not great, which is why we started having these ponds and everything, and that's how that all started. So why is salt water bad for freshwater fish and other organisms? I mean, we've heard it all the time, salt water will kill freshwater fish, and kind of vice versa too. And it's pretty simply put because they're not used to it. But if we want to dig a little deeper, it's due to the semi-permeable membrane that are around the gills that fish have. So what essentially happens, if you're familiar with osmosis, is that when salt is added into the water, it changes the concentration of the particles in the water. And what ends up happening is a freshwater organism will actually have less dilute water in its body than is in the environment. And due to that, through the semi-permeable membrane, what happens is the water will end up leaving the fish to try and balance that situation out. Even though it can't actually, there's no way the fish can excrete enough water to fix the fact that there's more particles in the natural water. But what will end up happening is the water will get released, and the fish will actually end up essentially becoming dehydrated and die. And it's and the way that that's generally supposed to work is that we got the blinds effect going on me again here. The way that it's generally supposed to work is when you have water that's very fresh, so fresh water with not as much particles in it, because fish naturally have some salinity to them. They have some obviously particles in them. They're it's not pure water that they're made up of, right? That will actually balance out. In a normal situation, the water would be forced into the fish. When you add salt into the water, it reverses that system, and then the water wants to leave. So in Canada alone, over 5 million tons of road salts are applied to roads every single year. And a third of streams and rivers in the US have become saltier over the past 25 years. Increased urban growth is a leading cause for more road salt usage, which makes sense, right? If you have areas where they were rural and there was actually nobody living there, you're not going to be putting salt down on the non-existent roads there. It's as soon as we start building up those towns, building up those cities, and then those people that live there want that, nice paved road, or they want that snow and ice off of the roads, reasonably so. I'm not saying that we shouldn't be, getting rid of the ice off the roads, but they want that off, and as a result, salt is put down, and then we have the issue of salt being in our environment. Salt use also does not just affect the environment as bad as it is. It also affects just our infrastructure. It increases erosion of rebar within concrete, and it can also contribute to structural damage to infrastructure, such as bridges and overpasses. So salt can remain in soil for decades, which can also impact our groundwater sources, as well as ecosystems long after the use of that salt. So there's salt even in the ground that we have now that's just been flushed off of the roads that didn't make it to, say, a stormwater pond. And if it's sitting in the soil, and say we just decided arbitrarily we're not going to use salt at all anymore, period, and we're done with it, we would still see impacts of salt getting into our groundwater, getting into our lakes and rivers for at least a decade, just because of the salt that's just been sitting in the soil, making its way slowly through just the water slowly pushing it along. The next one is coral reefs. And I just want to have a picture showing this first off, just to show how beautiful they really are. If you have not had the opportunity to snorkel or scuba dive amongst coral reefs once in your life, especially now that stuff is starting to open up again and flights are becoming a little more commonplace, I recommend it. Once you do it, you'll probably struggle to think of something that's just quite as breathtaking as coral reefs can be. So in a nutshell, I've been using that word a lot lately. I guess that's my new tagline. It's a coral reef is actually a vast colony of animals that grow extremely slowly. If you were to actually look at them under, not like under, a microscope or something like that, you would see these polyps, these little tiny things here, as opposed to just stone and brick almost is what they kind of almost look like, right? They're home to millions of species of marine flora and fauna as well. It's not just about the coral reef itself, it's about all the different animals that it supports as well. Anybody familiar with Finding Nemo knows exactly what I'm talking about. They only grow in very specific conditions, coral reef. They need these specific conditions to exist. Water temperature between 23 and 29 degrees Celsius. It requires very salty water, so kind of ironically the opposite of what we were just discussing with salt entering our fresh water. And water must be clear to allow sun penetration. And the reason for that is because some of the algae and microscopic creatures that help the coral reefs actually use that sunlight through photosynthesis to create energy for the coral itself. So how does climate change actually impact coral reefs? These are the big ones. So warmer oceans from climate change contribute to chloral bleaching and infectious disease. Chloral bleaching is when the algae living in the coral is expelled, which turns the coral completely white. The algae, which are actually called like zooxanthellae, are the ones that are doing that photosynthesis that I was discussing just a moment ago. Bleached coral is not actually dead, but it is under severe stress and it's subject to death and mortality. If temperatures remain high, which with climate change they would, the coral does not let the algae back, and then the coral would die as a result. Sea level rise can also contribute to increases in sedimentation, which is just more particles and sediments being buried into your water, and it smothers the coral as well as reduces sun exposure because the sun just can't penetrate through all that particles. And also, just buried in sediment is not going to be good for the coral's health either. Changes in storm patterns can lead to more frequent and severe storms that can destroy coral reefs, as well as create algal blooms that reduce sun exposure. We're going to be discussing algal blooms in just a moment. They're also a pretty important danger that we should be aware of. Altered ocean currents. We discussed briefly in a couple of lectures ago how one ocean current has been impacted by climate change and has decreased in decreased in how effective it is. It reduces connectivity as well as water temperature because a lot of these ocean currents flow and allow for the transfer of temperature and energy. It can reduce food for the coral as well as coral larval dispersal. And then finally, ocean acidification can cause a reduction in pH levels and decrease coral growth and structural integrity. So algal blooms. Algal blooms are, in a nutshell, basically I keep saying nutshell, I gotta stop that. They're basically a party gone wrong. So the way that you can think of an algal bloom is they can occur in both freshwater and saltwater environments, and they're caused by the same thing, excess nutrients. So this is where it's the party gone wrong part. These excess nutrients cause the algae to grow rapidly and out of control as they now have this gigantic amount of resources to eat. But algae, not the smartest of creatures, obviously, and they don't know how to really ration the food that's available to them. And so once all of those nutrients have been eaten up, the algal bloom has nothing left to eat. And they all basically start starving and dying. And you get this mass die-off. And the dead algae begins decomposing in the water. And this act of decomposition actually consumes dissolved oxygen in the water. It can create what's called a dead zone, where the decomposition has removed all the dissolved oxygen in the water. And as you can imagine, any fish or other aquatic creature or critter that needs oxygen to breathe in the water, they can't survive there anymore. And so it can actually cause either migrations of animals away from that lake or that spot in the water, or it could just cause suffocation and the creatures themselves die. These excess nutrients themselves, to kind of, roll back a little bit, are usually derived from things like fertilizers used for agricultural or recreational purposes, and they end up getting flushed into our water bodies. This is actually another thing with the sedimentation that I was talking about, where you have salts being run off from the roads, but you also have sand being run off from the roads, because sand is actually excellent at collecting particles such as phosphates, such as nitrates, and those are super yummy to plants. They love that stuff. So even just stuff like sediment being thrown into the water, and extra sand being thrown into the water, can be a catalyst towards having more algae and more algal blooms growing. The coral reefs, coming back to them for just a moment, they are home to a vast number of marine life. Again, not a surprise to anybody. You see any picture, even this picture here, you see different fish floating around. The destruction of these coral reefs removes a home for all of these species, and the coastlines can also become more susceptible to damage and flooding, because coral reefs can actually also act as a bit of a buffer, preventing the storm fronts from actually impacting the coastline as badly as they do. And then the oceans can't absorb as much carbon dioxide as a result too, because these can actually act as a sequestering areas for carbon. And we got this nice video I'll just take myself off for.
A state of emergency in Florida.
The worst outbreak in years of toxic algae.
Green, slimy, smelly, and flat out dangerous invasion.
100% horror.
Manatees struggling to move.
Thousands of dead fish.
Dolphins, sea turtles, even a 26-foot whale shark.
Some residents complaining of headaches, respiratory issues, and even rashes.
The pungent algae bloom stretches for about 150 miles,
growing bigger and lasting longer than years before.
It is a crisis that's happening as we speak. So it's important as a scientist, when you see something happening, that's when you need to act. All algae are basically plants. They need three specific things to survive. They need plenty of light, warm temperatures tend to make them grow fast, and they need nutrients, just like any plant, any house plant, any plant you see outside. When they start to grow into these very large nuisance blooms, we have to ask ourselves why. And in most times we would answer that we've changed the conditions ecologically which allow them to exploit the conditions and grow. Most of the driving factor for harmful algal blooms relate to nutrients. It is a fertilizer. Just like you fertilize your lawn, if you fertilize the ocean, certain plants are going to grow better. Unfortunately, these algae, which are, tend to be harmful, are the ones that grow better, and they can take over a system. So even though they're naturally occurring, we're contributing to the damage they do.
I love the earth. I really hate to see it changed. I mean, I've been in South Florida all my life, and I wouldn't swim in Lake Okeechobee anymore. I don't swim in the Intercoastal anymore. In fact, I very rarely even think about going in the ocean here anymore. And it's somebody's got to look at it, and I'm just glad that I can do a little.
How deep do you want the water sample? Down near the bottom, I assume?
Take one about a half a meter, and then one just above the bottom. The unknowns in these blooms is we've got a pretty good handle on, yes, it's nutrients. We need nutrients. But what actually, when there is plenty of nutrients and there's no bloom, why not? What kicks that bloom on? What actually starts it? Okay, so is it iron? Is it some other little factor that we don't know yet? Copper, zinc, there's a lot of so-called cofactors for enzymes, okay? But what is the actual trigger, okay? Because there's been times where it's been calm and hot, and you test the water and there's nutrients and there's no bloom.
The nutrient sources that can drive these blooms are really varied, so it's hard to pinpoint what is the biggest offender. You know, is it agricultural? Is it septic systems that are not controlled well? Is it people fertilizing their lawns and runoff from their grass fertilizer? Is it golf courses? Who knows? There are many inputs of nutrients around the state of Florida. Trying to figure that out is one of the biggest puzzles that scientists have to do. The biggest thing that the public can do to help us out in understanding harmful algal blooms are to contact their state and federal representatives to push action, to make sure that legislation and any bills we can get through to help us get the funding and the resources we need to do this work are supported. We need as much support as we can get. Science is expensive. This algae that's the current problem that we want to study in Lake Okeechobee occurs all over the world. It's a big problem in Lake Erie and has been for many, many years. Any techniques we develop here can easily be used in these other areas. We like to have our waterways and our oceans be clean and be able to enjoy them. And if we don't do something, we're going to lose it.
Okay, there's a couple of important points in that one too that I wanted to quickly touch on. It's cool how, well, not cool, I guess that's the wrong word to use, but it's important to also remember that even though I was talking about how the algal blooms will impact the aquatic species that are living there, they'll obviously also impact us. Not just because we might fish those fish or we might want to swim in those waterways, but we can also, as you can see, get toxic rashes and headaches and actual physical health related issues because some of these algal blooms, the algae actually, some of them release toxins too. And you can imagine when you have a bigger population like a bloom or a growth like that, it's just that much more dangerous. It's something that I want to stress, probably one of the most important things I'm going to stress in this entire course, honestly, is the saying that the dose makes the poison. So what I mean by that is that it kind of goes for everything, right? A single algae is not going to, even if it creates some toxin, is not going to do anything to you. 100 might not, 1,000 might not, 1,000,000 will. It's the same thing with salt on the roads. If you have just a little bit of salt, it might be manageable, especially with stormwater management. Start putting more salt down on the roads, might be manageable. More salt might not be manageable. Even more salt, it's not manageable. It's all about hitting that important point of no return, essentially. It's basically the idea of we can have our cake and we can even maybe eat it too, but we just need to be careful about how much of the cake we're making, if that kind of makes sense. It's important to keep in mind, as I said, the dose is what makes the poison. The dose is the important thing. Yeah. Oh, we go right into another video here. This one I believe is about... Oh, I'm not going to waste time. Let's just find out.
A state of emergency in Florida.
The worst outbreak in years of toxic algae.
Green, slimy, smelly, and flat out dangerous.
Am I?
A state of...
Yeah, never mind. That's a different one, but you know what? I'm going to skip that because I don't know why I have that in there. I'm not going to do 2 videos on algae. So rising sea levels is our next topic here. This is an important one. It's probably one of the more popular ones that people are more aware of too, as far as climate change, global warming, and all of that is involved. You probably heard it in the news, you probably read about it in articles, you probably read it in textbooks and whatnot, and heard it from friends and family. The sea levels are rising. And in fact, since the 1880s, sea levels have risen 8 to 9 inches. This chart that is just to my left here is showing just how much they've risen roughly since the 1880s, with 0 being the 1993 to 2008 average. So in 2020, global sea level set a new record high of 3.6 inches above 1993 levels. The rate the sea level is rising is actually accelerating, and that's the important part too. If it was a consistent increase, that's obviously still not great, but at least then it's something that could manageably be dealt with. Maybe it would be something that was more naturally occurring. The fact that we're seeing it accelerating is an issue. It's showing that there's like those cumulative returns on things that are happening. So the 20th century, for instance, saw a 0.06 inch increase per year, while 2006 to 2015 saw a 0.14 inch per year. Might not seem like a lot, but that's per year, every single year. So even with drastic decreases to greenhouse gas emissions, sea levels will still likely raise at least 12 inches above 2000 levels by 2100. So in about 80-ish years, our sea level is going to be about a foot higher than it was in 2000. A worst case scenario, and this one's scary to think about, with high emissions that aren't really controlled, we could see as high as an 8.2 feet above 2000 levels by 2100. Got to add another 0 there. I'm 6 feet. I'm 6'1". So that's taller than me. I'd be underwater if I was standing on the beach by the ocean, as I were right now, and it teleported to the year 2100. That's a lot of extra water. You can imagine how much damage that would do to infrastructure. In the United States alone, almost 30% of the population lives in high population dense coastal areas, which are prone to flooding, to shoreline erosion, and hazards from storms. This just makes sense. If you think about some of the most populated cities in the world, New York, Los Angeles, Miami, they're all by the water, right? People love water. We need it to survive, but it's also fun for a lot of extracurricular activities. It's good for ports so that we can transport goods. It's part of who we are. Globally, 8 of the world's 10 largest cities are near a coast. So rising sea levels obviously threatens this city infrastructure. Roads, bridges, subways, water supplies, oil and gas wells, power plants, sewage treatment plants, landfills, etc., etc., etc. All of this stuff can be impacted by rising sea levels. Some of them more obvious than others. Power plants, you don't want water getting in your electrical stuff. Roads, bridges, subways, water supplies, they'll just deal with erosion, and just being put underwater is obviously not great. Extreme storm events like hurricanes can travel even further inland too. We're going to discuss that a little bit in a second too. But hurricanes gain power or strength based off of being over top of the water and drawing moisture from it. So you can imagine if the water level rises such that where land and water meet is now further inland, hurricanes are going to be able to travel further inland than they could in the past. There are 3 main contributors to rising sea levels, and they're kind of ordered in terms of magnitude of how much they're actually contributing to rising sea levels. So first off, we've got our melting of glaciers and ice sheets, which adds water to the oceans. Another important one, this is more for the chemistry people, the volume of the ocean actually expands as water warms. You can think of this as temperature of a solution or just a chemical in general increases, it expands, it gets bigger. You can see that even just as when when water turns into steam, it expands even more. It's hitting its next transition state. When you see that with water, colder water is actually more condensed, and then as it warms up, it spreads out a little bit. And then finally, the third contributor is just the decline in amount of liquid water found on land. So we're finding more water in our oceans than there is on land. It's just that kind of part. And that also goes to do with glaciers and ice sheets as well. So this chart kind of explains it a little more. So sea level is measured using tide gauges and satellite altimeters. Okay, so tide gauges measure daily high and low tides, and they've done this for more than a century. Scientists calculate a global average, and then they adjust it for seasonal differences. Since the 1990s, Sea level has been measured from space using radar altimeters, and the way that that works is kind of like Doppler, kind of like an ultrasonic sensor in a way, if you want to think of it that way. A radar pulse is directed at the ocean, and based on the return speed and the intensity, the sea level height can be determined. Thermal expansion is measured by using moored and drifting buoys, satellites, and water samples collected from ships. And then temperatures in the upper half of the ocean are measured by a global fleet of aquatic robots. Deeper temperatures are measured by instruments lowered from oceanographic research ships, such as the Argo floats that we discussed a few weeks back. And then that mass transfer, that third point that I discussed just in the last slide, this one here, the declining amount of liquid water on land. It's estimated by direct measurements of melt rate and glacier elevation made during field surveys, satellite-based measurements of tiny shifts in Earth's gravity field. When water shifts from land to ocean, the increase in mass in the ocean itself, the water, increases the strength of gravity over the oceans by just a small amount. But because of these gravity shifts, scientists can estimate the amount of added water. Next topic is invasive species. So as I said, we did discuss this last week, but we basically were talking about last week terrestrial creatures that were invasive. So mostly our plants and, creatures that live on land. Aquatic species are a lot more limited by their surroundings. If there's no river or aquatic path to take to a lake or other water body, they're kind of SOL, right? They don't really have a way to get to that spot. Through the expansion of humans, creating rivers, creating canals, expanding rivers, just to allow passage of boats, has allowed creatures to travel in ways they normally couldn't to reach locations that were previously inaccessible. Zebra mussels and sea lamprey are actually two excellent examples of this. Invasive species can basically be boiled down as creatures taking advantage of a new environment. They either disrupt the food chain entirely by outcompeting other predators, or they destroy the environment to prevent other creatures from surviving, or they just predate on everything in general. So it's usually one of those three ways. So this is the zebra mussel. If you're not familiar with it, you probably haven't been spending a whole ton of the time in the lakes around Ontario. So they likely arrived in the Great Lakes in the 1980s via the ballast water that was discharged from large ships. Previously, they had no other way to get there. Zebra mussels are actually indigenous to Russian lakes, so they're a long ways from home. Zebra mussels filter out algae that native species use for food. Zebra mussels also attach to and incapacitate native mussels. They also accumulate pollutants and toxins, making them dangerous to consume, and are believed to be responsible for the poisoning of thousands of birds in the Great Lakes, and they also clog water intakes. The removal of algae and other particles in the water is so effective they can actually increase the region of water that sunlight can reach through, which also adjusts things such as the thermocline, which is something we'll discuss in a second. It's basically a layer of water in the lake, and which will determine how deep algae can actually grow. In some extreme cases, this can remove the lower layer of the water, which is called the hypolimnion, entirely, which would have drastic impacts on the ecology of a lake. And then we've got the sea lamprey that we're going to talk about for a second here. I'll get myself off for this too.
The sea lamprey is only one of nearly 200 non-native species in the Great Lakes, but it's a nasty one that has taught us valuable lessons.
What the sea lamprey does is, with this suction cup, attaches to adult fish to grind off the scales and then flesh so that they can literally suck the life out of adult fish. This highly specialized parasite could literally wreak havoc on fish populations in the Great Lakes, and of course that's exactly what it did.
Sea lamprey invaded the Great Lakes from the Atlantic Ocean nearly 200 years ago when we opened shipping canals. Niagara Falls held the attack until the opening of the Welland Canal. By the 1950s, the invasion was complete. Their populations exploded. Commercial fisheries were decimated. So the American and Canadian governments joined forces and created the Great Lakes Fishery Commission to study the sea lamprey, learn its weaknesses, and take action to control it.
Quite frankly, The Great Lakes Fisheries Commission, as a result of that joint effort by both federal governments, has led to what can only be described as one of the greatest success stories that North America has ever seen.
Cooperative research certainly paid off. We learned how to control sea lamprey. Populations have been reduced by 90% in most areas using a variety of innovative techniques. Barriers prevent lamprey from spawning. Releasing sterile males reduces lamprey reproduction, and a selective lampricide kills only sea lamprey larvae. Control is costly, but an ongoing necessity to protect the $4 billion Great Lakes fishery. To learn more, call the Invading Species Hotline or visit invadingspecies.com and help keep all our lakes great. This message is brought.
So I actually did some research back when I was in university on this very topic on sea lamprey, which is part of the reason why I brought it up too, because it's also just an interesting topic, but they're ugly little creatures, eh? The point that's important to bring up is that the selective lampricide that they mention, it's not as selective as they like to try and advertise it as. It can and does kill other creatures in the lakes as well too, especially younger spawnling creatures that aren't as robust yet as the adult version. Lake sturgeon are a big example of something that's a little more sensitive to these lampricides. But yeah, sea lamprey are definitely a threat that was something of our own creation, basically, when we expanded the Welland Canal and allowed them to get in. If you want to learn more about them, there's a whole lot of research done on sea lamprey and just the impacts they've had on the Great Lakes.
Brought to you by the...
Okay, so this is actually another video. I got a couple in this one, but this one is about how lakes cycle, and it's a good way to really visualize this next topic, because it's a pretty interesting and important one. Oh, my cat just freaked out. Sorry about that.
Nelson here with your Untamed Science podcast. Now, it's that time of year again, and that means that our lakes and our ponds are changing. But do you know what that means?
The ever-changing lake.
I grew up on a lake. In fact, it was the lake that I spent hours and hours skiing on that made me fall in love with biology. So I think it's really important that everybody knows the truth about how lakes work. So today we're giving you a crash course. Of course, the first thing that you have to do is you have to know how to talk intelligently about the lake. And it turns out there's a lot of different zones in the lake. You have the nearshore littoral zone, the open water limnetic zone, the deep water profundal zone, and then at the bottom of the lake, the benthic zone. While we're talking about this, it's important to note that not all lakes are the same. One of my favorites, Lake Michigan. In fact, it's so big that you can actually dive on huge wooden ships. And a lake like that gets mixed really well and harbors a ton of life. But you visit that lake in the winter and it's covered in ice. Other lakes include warm, swampy lakes, small ponds, giant tropical lakes, and beautiful mountain lakes. So that's a lot of lakes, and some of them are pretty different. But since most of you live in the temperate zone, let's look at a typical temperate lake like the one I grew up on. Now, a typical temperate lake will cycle year after year. In the summer, the sun heats up the surface water, and the wind helps circulate the surface, but a thermocline develops and cold water stays deep. Then, in the autumn, the surface water cools, allowing the lake to circulate. In the winter, ice forms at the surface with the warmer water underneath. As the spring comes, the water warms and the lake turns over again. Remember though, if we don't have a period of cold, the lake won't cycle. For instance, this is Lake Gatun on the Panama Canal. I lived there for about 6 months, and despite having to deal with crocodiles, there is a difference in that lake. The difference really is that the lake doesn't cycle. The surface doesn't mix with the deeper cold water, and that water remains anoxic. Now the other thing to remember is that any lake will never be around forever, because a lake is actually slowly getting filled in. You see, it works like this. Take this small lake here in the forest. It will slowly accumulate sediment as debris and other material falls into the lake, and then those sediments build up. Over time, they become marshy areas, or will eventually disappear forever. And of course, it's kind of fun to realize that in the grand scheme of things, you're on a lake that's only around for a very short period of time. Pretty cool, huh?
Okay, and you're probably sitting there thinking, what's this got to do with climate change? What's this got to do with environmental concerns or anything, right? Well, it's a valid question. So lake turnover. This is essentially the important part that he was talking about from that video. You got your 3 layers. You don't need to know about the benthic zone and the profundal zone and all that stuff. The 3 here are the important ones. You got your epilimnion, your thermocline, and your hypolimnion. The epilimnion is typically the area where sunlight can reach and be exposed to, which is why it's the warmer area. The thermocline is that border where sunlight no longer reaches, and as a result temperatures drop. You can see that based on here, right? 22, 20, 18, 8, 6, 5, 4. It's a lot lower in this area. And for the most part during the summer, these layers are very static. They almost are treated as almost as if they're 2 separate bodies of water. They don't really mix, they don't really interact with each other very much. But then the fall happens and everything cools down, and you get this turnover, and that means that everything can mix and combine and shove around all over the place, and that's really important. And then you have the winter, when the ice is formed, and you have your bottom area, which is actually now the warmest, which is 4 degrees, still not warm, but warmer than the cool 0 you've got right there. And then finally it gets to spring, and there's the turnover again, and then back to summer. So why is this important? Well, it's important because it allows for the cycling of nutrients and oxygen throughout the entire lake. If you had this situation, and he hinted at it in the video when he said that the bottom area of that the lake that was like in a rainforest or tropical location, the bottom layer, the hypolimnion, was actually anoxic, which means there's no oxygen present there, and that's bad. For that lake, it might not be a big deal because it's super warm there year round. But without this cycling that we have, life would not exist in our lakes as we know them today. It provides an area aquatic creatures can hibernate over the winter due to the freezing of the top layer. If we didn't have this mixing and the water froze over, what would end up happening is the fish at the bottom would die. They would go to hibernate here, and it'd be an anoxic area with no oxygen, no nutrients, no nothing. So that turnover is super, super important. And with climate change happening, you start getting warmer summers, or you might just get colder and colder winters. And as a result, this can actually be threatened. All right, so our next topic is extreme weather events. This chart here is showing how extreme weather events, this is not just aquatic events, mind you, as you can see, forest fires, droughts, mass movement, stuff like that. That's all involved in this chart. But as you can see, basically from 1980 all the way to 2014, we've had a pretty noticeable increase in the amount of extreme weather events. We've gone from 291 in 1980 to 904 in 2014. That's like over 3 times as much. It's pretty extreme. Not pun not intended. So first off, we'll talk about hurricanes. So warmer sea surface temperatures can intensify storm wind speeds. That's important too with climate change, as I mentioned before. The National Oceanic and Atmospheric Administration, or NOAA, has hypothesized that an increase in Category 4 and 5 hurricanes with wind speeds increasing up to 10% due to the theorized models of what climate change is going to cause. Warmer temperatures can also increase the amount of precipitation. If you look at a couple of these more recent hurricanes, Hurricane Harvey in 2017 dropped over 60 inches of precipitation in some areas. Hurricane Lane in 2018, which landed in Hawaii, dropped over 52 inches of precipitation in some areas. And then Hurricane Imelda in 2019 dropped over 44 inches in precipitation in some areas. These high amounts of precipitation demonstrates the devastating floods that can also be triggered by hurricanes as well. So sea level rise will make coastal storms more damaging. I touched on that briefly when I said that with higher sea levels, what will happen is that storms will be able to move further inland before they'll start, losing power or losing steam, I guess, for a better way of putting it. Another thing that I forgot to mention when I was saying the rising sea levels, but with all these people, like as I said, 8 out of the 10 largest global cities are located on coastlines. if you have the sea levels rising, people are going to have their houses flooded and they're going to have to move. You're going to start seeing mass migrations potentially of people leaving these coastal cities to move inland, and that's a whole other problem and a whole other kerfuffle all in itself for these nations and these countries to try and deal with. With coastal storms being more damaging due to the sea level rise, coastal storm surge will allow them to travel further inland than previously. Storm surge is basically that water just being pushed in further. It's what causes the floods. Sea level rise intensified impact of Hurricane Sandy, which caused an estimated $65 billion in damages in New York, New Jersey, and Connecticut in 2012. That $65 billion is actually adjusted for 2020 inflation, but it's a lot of money. 4 of the 10 most costly hurricanes on record in the United States occurred in 2017 and 2018. So things are not getting better. Things are getting a lot more dangerous. And Hurricane Katrina in 2005 is the most costly at $168 billion in repairs. So floods, the accumulation of water over normally dry land. That's a pretty succinct definition for what a flood is. It's caused by an overflow of inland waters or tidal waters, or by an unusual accumulation of water from sources such as heavy rains or dam or levee breaches. So if you have river flooding, most common in lake water and in late winter and early spring. Jesus, my typing there. It results from heavy rainfall, rapidly melting snow, or ice jams. This is an example, this picture here, of an ice jam. You can see all the ice just kind of piled up here. And then what happens is water basically has nowhere else to go, and it's forced to basically go over into people's backyards, essentially. This is a storm surge. So coastal floods. It happens when winds from coastal storms such as hurricanes pushes a storm surge from the ocean onto land. So a high tide flood, which is also known as a nuisance flood, occurs when the sea washes up and over roads and into storm drains as the daily tides roll in. They're also known as nuisance tides because they aren't especially dangerous, but they're common enough and costly enough that they're just really annoying problems to deal with. So this picture is showing, if you see the mean sea level where it normally sits, 2 foot normal high tide is right there. And then there's the storm tide. So that 15-foot difference between 17 and 2 there is your surge that's going to blast forward and, in this case, take out this person's house. Then there's flash floods. So quick rising floods that often happen due to heavy rains over a very short period of time. You remember those IDF curves from last week? Those 100-year storms, those high-intensity storms, they're the primary cause of these flash floods. They can happen anywhere, but low-lying areas with poor drainage are particularly vulnerable. And with climate change starting to change the patterns of where storm events can and will happen, this can make areas that were previously not threatened to become threatened. And these flash floods are the most dangerous of the floods because they happen anywhere and with very little warning. Urban flooding is also kind of linked with flash flooding, and that occurs when stormwater drainage capacity is overwhelmed due to the intense stormfall. So it happens when rainfall runoff is channeled from roads, from parking lots, from buildings and other impervious surfaces to the storm drains and sewers that cannot handle the volume. So the volume ends up flooding back onto the roads, which ends up flooding back onto the lawns, which ends up flooding into your houses and backyards and so forth. And that brings us to the end of this lecture. So this is basically what we're looking at here. Next week we're going to do the final exam review. So I'll put together a presentation just going over some of the details on the final exam. For a little heads up on it, it will be 50 multiple choice and true or false questions. That's all you're going to find in it. So 50 questions, which are a mixed match of multiple choice and true or false. You're going to have 2 hours for it. And as it says here on the thing here, it'll be available Monday, April 18th. As of One Ocean video assignment will be due Friday, April 15th. I put that video and the assignment up already for everybody to try and give everybody a little bit extra time. I realize with everybody's course loads that and exams coming up just around the corner, that everybody's probably a little busy, so I wanted to try and give a little bit extra time for that. I also apologize, this week's been pretty hectic for me as well. I haven't been able to get any marking done, but I'm gonna basically hunker down this weekend and just get right into it, so you can expect to see some of your marks starting to pop up for that stuff as early as Saturday or Sunday. So yeah, apologies about that again. As always, if you have any questions about anything, please feel free to reach out to me. I'm able to look at my Outlook pretty often, so I should be able to get back to you pretty quickly with any questions you have about that. But if you also want to meet up via WebEx or through what's the other, Zoom or something, just to go over some questions you have about especially the final test coming up, by all means, feel free to reach out and we can set something up. It's been a pleasure teaching everybody. I really hope that you guys have enjoyed this course so far. So yeah, I'll talk to you guys next week with the final exam review. If there's any topics that you want me to touch on some more, please also feel free to shoot me a message on that as well, and I'll incorporate that into the final exam review as well too. If there was something that you were interested in, something you just want me to go into more detail about, or just something you just think that would be beneficial to go over, shoot me a message on that and we can sort that out as well. So yeah, thank you everybody, and I'll talk to you all next week.